This is Dr. Jessica Dunn, and we're going to discuss increased compounding. So thus far in our discussions, we have compounded our interest annually. But in real life, interest is not usually compounded annually. It's usually compounded more frequently than that. For example, when you purchase a new car, the interest on that car is compounded monthly. Your payment is due monthly and the interest is compounded monthly. The same is true with real estate, and even the vice versa is true. So savings accounts. Savings accounts pay interest monthly rather than annually. So the result of compounding more frequently than once per year is that the effective interest rate is higher than the nominal. And what that means, the effective interest rate is basically the rate that you're earning or paying. So you're actually going to earn more interest or pay more interest when we were talking about a debt than is contractually stated with the nominal rate. So the nominal rate is the rate that we have been discussing. It's the rate that you plug into your time value of money functions on your calculator. It's the rate that's given on loan agreements. And the greater the compounding frequency, the faster the effective rate increases. So here's the equation for compounding more frequently than annually. And this is similar to what we said before. Before we said that the future value is equal to the present value times 1 plus r raised to the nth power. That looks very, very similar. The only difference is that we divide by m and multiply by m. So what is this m? M is the compounding frequency. So m is the compounding frequency. And thus far in our discussions, we have talked about annually. And if we're talking about annual, the m is 1 because there is one annual period per year. So if we said semi-annually, then our m would be 2 because there are 2 semi-annual periods in 1 year. Quarterly, m is 4 because there are 4 quarters in a year. Monthly, m is 12 because there are 12 months. Weekly, m is 52 because there are 52 weeks in a month. So you can see how this progresses. M is just how many times is that time period divisible into a year. So let's look at that Fred example that we've been discussing. And if you haven't seen that, then the Fred example is Fred deposits $100 into a savings account that pays 8% interest. How much would he have at the end of 1 year? And we had said that if interest was compounded annually, Fred has $108. But what if the interest is compounded semi-annually? So the equation would look like this. The future value would be equal to the present value, or the amount initially deposited, times 1 plus the stated rate, 8%, divided by the compounding frequency, semi-annual, so that's 2, raised to the compounding frequency times the number of years. So that is 100 times 1 plus 4% squared. And so if we were to work this out, we would see that at the end of the first year, he would have $108.16. So he actually has 16 cents more with semi-annual compounding than he would have with annual compounding. So our interest is growing faster. Our effective rate, the rate that we're actually earning, is greater than the nominal rate because the nominal rate is 8% and 8% of 100 is $8. And now instead we're getting $8.16. That's a result of increased compounding. And the greater we increase the compounding frequency, the more money you would have. So here's that $100 at 8% compounded semi-annually for 2 years. You would have $116.99. If this were compounded annually for 2 years, then you would have $116.64. So you get an extra 35 cents because of this increased compounding frequency. So what if interest were compounded quarterly? How much would he have at the end of 1 year? So if interest were compounded quarterly, then our M would be 4 because there are 4 quarters in a year. So that's 100 times 1 plus 2% raised to the 4th power. And that would leave us with 108.24. So when we said we had semi-annual compounding at the end of 1 year, we'd have 108.16. With annual compounding, we'd have 108. With quarterly compounding, we have 108.24. So our effective rate is increasing. We're actually earning more than what is stated. And so here we see this. If we have annual compounding versus semi-annual versus quarterly. So at the end of the second year with annual compounding, we'd have 116.64. With semi-annual, we'd have 116.99. And with quarterly compounding, we'd have 117.17. So the greater the compounding frequency, the more periods we get in a year. So if we got down to seconds per year, then you would have more money at the end of the second year than you would with quarterly compounding. So the smaller that time period, the faster that interest is being added to the principal, the more money you have. And the opposite is true. If this were a loan, the smaller the compounding time, so the greater that interest is being added to the principal, the more you're actually paying. We could get all the way to continuous compounding. So continuous compounding is a theoretical property, but I can't think of any examples in real life that would have continuous compounding. Continuous compounding is where interest is added to your principal an infinite number of times per year, so microseconds. The equation for continuous compounding is listed here. The future value is equal to the present value times the exponential function raised to the interest rate times the number of years. This is not something that you can calculate on your calculator, so you do need to know this equation. The future value is equal to the present value times the exponential function raised to the interest rate times number of years. So what would be the value at the end of 2 years of this $100 invested at 8% if we had continuous compounding? So future value is equal to the present value times e to the interest rate times the number of years, e to the Rn. So he deposited $100, multiply that by the exponential function, raised to the 8%, and this is a formula. It is not your time value of money solver, so you do have to use decimal point interest rates multiplied by 2 for years. So let's go ahead and solve this. We have to do the exponent first, so 0.08 times 2, solve for that. Then we need to use the exponential function, which is right next to the number 7. It's that e to the x right there, right above natural log. So we push second e to the x, then multiply it by 100. And we get 117.35. So if you compound it continuously, then your $100 at the end of 2 years would be worth $117.35. Remember, with quarterly compounding, it would be worth $117.17. So the smaller the time period, the greater the compounding frequency, the greater the effective interest rate. So let's learn how to do this on our calculator. So let's do this same example. Fred puts $100 into a savings account paying 8% interest. How much would he have at the end of the second year in the following circumstances? Annual compounding, quarterly compounding, and monthly compounding. So let's first discuss the inputs and how they're going to change based on compounding frequency. So when we looked at the formula, remember the formula said that the future value is equal to the present value times 1 plus r divided by m raised to n times m, years times compounding frequency. So you see in the formula there are only a couple of items that change. Our exponent changed, so now we need to take years times compounding frequency and put that in our calculator. Our rate has changed, so we need to take our stated rate, divide it by compounding frequency. Present value is the same. Future value is the same. And our payment is the same. No change. So let's work these examples on our financial calculator. So with the annual compounding, our M is 1. So he puts $100 into his savings account. Present value is $100. That savings account pays 8% interest. So with annual, it's 1. So it's still 8%. IY is 8. It's 2 years, and the compounding frequency is 1. So 2 times 1 is 2, and that's N. And we have no payment. So let's compute the future value. We get 116.64. So our N is, 2 times 1. Our IY is 8 divided by 1, so 8. Our present value is 100, and you can put a negative in there if you're thinking about it. He took it out of his pocket to put it into a savings account. Our future value is what we're wanting to solve for, and our payment is 0. And we got 116.64. Okay, so let's do quarterly. Let's talk about it first. With quarterly, our years is still 2, but our compounding frequency is 4 because there are 4 compounding periods per year. So N is 8. Our IY, our interest rate is 8. We divide it by 4, so we have a periodic rate of 2. Present value is still that $100. Our payment is still 0, so let's solve for future value. So first I'm going to clear my time value of money. I have 8 periods, a 2% periodic rate. Put $100 into the account and nothing else. So compute the future value and we get 117.17. Monthly, there are 12 months per year. So our N is 2 years times 12 months to give us 24 periods. Our IY is 8% divided by 12. Our present value is a negative 100. Payment is 0. And let's solve for future value. Okay, so first step, clear our time value of money. We have 24 periods. 8 divided by 12 is 2/3. That's our interest rate, our periodic rate. We put $100 into our account. No payments. Compute the future value, and we get 117.29. So let's do an additional example. How much would you deposit today to have $500 in 1 year if the interest rate is 5% compounded monthly? So we want to know how much would we deposit today. In 1 year, we would have $500. But interest is being compounded monthly, so we'd have January, February, March, April, May, June, all the way to December. So we are going to be receiving monthly interest payments on our deposit. So dot, dot, dot there, all the way to December. So for that, we need to set up our problem. We know that N is M times N. IY is our rate divided by our compounding frequency. Present value is the same. Future value is the same as before. And our payment is the same. So in this example, if we put if we wanted to have $500 in 1 year, then our future value would be 500. We want to have that money in 1 year, and we're compounding monthly. So there are 12 months in a year. So 12 times 1 is 12. Our rate, we have a 5% interest rate. We divide that by our compounding frequency of 12. We're wanting to solve for present value, and we have no payments, so there's no recurring cash flows. So let's solve for present value. So we want to have 500, where it's going to compound for 12 periods. Our interest rate is 0.417 each period, and we have no payments. Compute our present value. If we deposited $475.66, we would have $500 in 1 year. And again, that negative is for interpretation. That $475.66 would leave our pocket, and in 1 year we would put $500 into our pocket. Let's do one final example. Let's say we were to deposit $150 every month into an account earning 9% for 20 years. How much would you have? So on our timeline, we have nothing in our account today. And every month we're going to deposit $150. And we're going to do that all the way for 20 years. So we're going to do 20 times 12 times. We're going to put $150 into that account. So our N would be M times N. We have 12 months times 20 years. Our interest rate is our stated rate divided by our compounding frequency. So 9 divided by 12. Our present value is 0 because we have put nothing into that account today. And our payment is $150 and a negative because every month we're going to take $150 out of our pocket and put it into this account. So let's solve for future value. So 12 times 20, 240 periods, 0.75 periodic rate. Nothing in the account today. We're going to deposit $150 every month. So that's equal, finite, and periodic. And compute the future value. We have $100,183.03. Let's assume that we did it for 35 years. So 35 times 12. It's 420 periods. Then we would have $441,267. So you see how fast that money starts to grow? That's the effects of compounding interest.